Astronaut problem 3 ways. After today, it's going to go from here to here. Yeah. Okay. You know, actually, I think I did that one in class, if you look back through the notes.
Yeah, you did 17.
Oh, okay, sure. Yeah. Okay. Let's do it.
It's 16.
Okay, but it's... Okay, and then what's the mass? 50. And then, does it say anything about... Radius is 0.1? Okay.
And part A is to do the pulley shown as weightless, and then part
Okay.
B is to do it.
Yeah, just part B is okay, right? Okay. So first of all, where this leaves the pulley doesn't matter at all. You know, it doesn't give an angle or anything, but notice that the row vector is straight perpendicular to that force no matter where it leaves the pulley. And so that moment is just going to be, it's going to be counterclockwise, so positive moment arm of 0.1 times the force is 600, so it's just going to be 60 Newton meters. Okay, so free body diagram of the mass, the 50 kilogram mass. We have the weight down of 490.5. We have force up of T. I guess the biggest difference here is, or one of the big differences, is that if this has mass, you can't assume anymore that it's the same cable tension on the two sides of the pulley. So we can't assume that this is just going to be a tension of 600 pulling up on the mass. This is just a particle, so all we get from this is Newton's second law. And that says 0T plus 0 negative 490.5 equal to the mass times 0A. And so the first useful equation says T minus 50A is equal to 490.5. And I'll call that equation star. This is the problem that was on the quiz a week ago or something. And now we'll deal with the pulley. And that's a rigid body. Does it have a fixed point or not? Well, it's fixed to the ceiling, so we can assume that the center is fixed. And so the moment of inertia about the center is equal to 1/2 times the mass of 3 times the radius squared, which is 0.015. Yes! That dad thought I'd never amount to anything. I'm trying to keep you from Uh,
I see a good psychiatrist.
okay.
Actually, I was just saying.
Well, he's not very good at getting you to class on time.
No, he isn't.
Okay. And so we got this, and now free body diagram. Yeah. What do we have? We have the reaction force from the pin. We have the force T down, and we have the 600 Newton force there, and then we have the weight of the pulley, which is 3 times 9.81. So rho, force, moment. Yep. Yep. Yes. That's right. Yeah. Or vertically, yep. Okay, so the about point is the center, so that force R has no rho vector. Force vector is Rx, Ry. Moment is 0. The weight force, rho vector is 0. Force is negative 29.43. Moment is 0. The force T, the rho vector is positive 0.10. The force is 0, negative T. Cross product is negative 0.1 T. And then the 600 Newton force, rho vector, the way we have it drawn there, is 0.1. Negative 600, 0 is the force. And the moment is 60. There's a fixed point here, so we're not using Newton's second law. So the moment equation says 60 minus 0.1 T is equal to 0.015 times alpha. Let me reformat that. So we have negative 0.1 T minus 0.015 alpha is equal to negative 60. Make those all positive. Okay, so that's equation 2 star. And the last thing we have to do is use a geometric constraint. Well, you know, if you look at this now, we have 2 equations, but 3 variables. Those are T, A, and alpha. And so we're going to need one constraint equation, and that's going to come from the geometric relationship, the kinematic relationship between alpha and A. So yeah, I just need to think about the sign, but A Yes, right. So the relationship between A and alpha, um, and you know that the acceleration of the mass is going to be the same as the vertical part of the acceleration of the point where the cable leaves the pulley. So that's why it works. So A is equal to alpha cross R, and then this part we throw away because we only want the vertical. There's no centripetal acceleration of that hanging mass. And so this is 0, 0, alpha crossed with 0.100, and that is 0.1 alpha 0. And so, like you said, A is equal to 0.1 alpha. Or the third equation says A minus 0.1 alpha equals 0. And you don't, but it'll, if it comes out negative, then it accelerated down. So the signs will work out totally on their own. All we have to do is come up with, like, we assume one direction or the other, make sure that all of the other variables make that same assumption, and then if it comes out negative, it comes out negative. Right. That's right. Yep, that's right. Basically, that's just starting with this 3 equations and doing substitution, you know. And can we do this? Okay. Because I know this is on this problem, this is a confusing thing to a lot of people, is just like it doesn't give an angle. Like, how do we even know what that? It turns out no matter what that angle is, it produces the same moment, and it only comes into the problem through the moment. Since this has a fixed point, you know, all we used was the rotational equation. So this applies a different force vector to this depending on what that angle is. But we didn't use Newton's second law, so the force direction didn't matter. So you can do it like this, or do it as a horizontal or as a vertical or whatever. It all works out the same. Or you could just do it as a couple applied to the pulley, which is what it's doing. Any other questions about that one?
Do we get our quiz back?
Not from me. I don't know. I don't know if you got it back from anyone else, but okay. Now, astronaut. I like this one. You know what I like? You know what kind of problems I like? I like all of those. But one type that I like is I like problems where you can approach it multiple different ways. You know, like you can use different approaches and at the end compare your answers. Like it's a good, if you can think of, if you ever forget how to do something, you know, problems like this, and they don't come up that often, are a good way to remind yourself, you know, tell yourself whether you're thinking about it right or not, you know. We're going to do 3 different approaches to calculating the astronaut's acceleration, and they're all going to match. 2 of them are going to use rotating coordinate systems. I used to call it astronaut three ways, but that was, and I was like, yeah, exactly. Yeah, I hate talking to that guy. Leave me alone. Nude? Oh, no. There's going to be a new vice president of academic affairs, I think. But if there was a new dean, he wouldn't have any leverage to complain. That would be great. Yeah. Okay, so here's the astronaut. Good. The hair or the face, yeah. So we're going to have the x-axis pointing that way, y-axis towards us, z-axis up. And the first time through, we're going to assume that the coordinate system's fixed. At the hinge. The second one is going to be coordinate system at the hinge, rotating with the arm. And the third way is going to be the coordinate system at the midpoint. Rotating with the arm. And let's say that this is 5 meters. And let's say that the angular velocity vector is 0, 3, no, 0, 0, 3. And it's constant, so there's no alpha. Okay, so 0, 0, positive 3 is rotating this way. So the first calculation is the warm-up one. If that coordinate system's fixed, so the coordinate system is fixed. So the origin is not accelerating. The axes are not rotating. And so we're just doing a simple circular motion problem as this astronaut goes around the z-axis in a circle. So the acceleration is just equal to alpha cross r plus omega cross quantity omega cross r. Alpha is the 0 vector. Omega is 0, 0, 3. The r vector is from the center of the circular motion to the object, the point of interest, which we're just treating the astronaut like a particle. And so that r vector is 5, 0, 0. So the acceleration is 0 plus 0, 0, 3 cross quantity 0, 0, 3 cross 5, 0, 0. That's 0, 0, 3 crossed with, yeah. And so that is negative 45, 0, 0. So about 5 G's of acceleration. Does the sign of that acceleration make sense? Yeah, all we have is centripetal acceleration, so it needs to be towards the center of the circle, which is the negative x direction. Any questions about that? Oh, the origin. There are two ways the coordinate system can be non-inertial. One is the origin is accelerating around. You know, even if the axes keep the same orientation, the coordinate system is accelerating around, then you can't use Newton's laws. And the other way is for the coordinate axes to be changing orientation. So we kind of need to, as problems get more complicated with what the coordinate system's doing, you have to mentally keep track of, do I have to deal with an accelerating origin? Do I have to deal with rotating axes? So at least in my class, it has been for quite a while. I don't remember if I made it up or not. It's like a scripty O. Yeah, yeah. It's been 10 years now. It's hard to remember what reality was like before I started. Okay, so now, finally, a calculation with a rotating coordinate system. So for this one, the origin is still not accelerating. Nope. Nope. Anyone else think that?
I'm gonna rate theta.
Nope, not that either. That's true. But this time, the axes are rotating. So we will need to use the equation that says acceleration is equal to, how am I going to write this? So the observed acceleration plus the time derivative of the angular velocity of the coordinate system its position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity vector plus capital omega cross quantity capital omega cross p. So we are going to have to use that now. Yeah, we're looking at the astronaut the whole time. We're positioned at the hinge and we're just going around like this. And so we're not going to observe anything, you know. We're going to observe a position, a constant position of 5, 0, 0. And we're going to observe a velocity of 0 and an acceleration of 0. Right, yeah, like what's this guy screaming for?
Such a win.
Yeah, exactly. Yes, because that's what we can use in Newton's second law. Okay, so let's just go through and figure out what all of these variables give us. So the position vector is 5, 0, 0. The observed velocity vector is 0. The observed acceleration vector is 0. The arm is moving with an angular velocity of 0, 0, 3. And so now that's what our coordinate system is also doing. So capital omega is equal to 0, 0, 3. And that's a constant angular velocity. And so capital omega dot is 0. Capital omega is of a coordinate system, and lowercase omega is of a body relative to the coordinate system. In this case, there's no lowercase omega, because relative to the coordinate system, we don't see anything moving. You know, if this astronaut, and eventually we'll get into problems like this, because if there was a wheel on the end of this spinning like this, okay, then our coordinate system wouldn't see objects on this wheel doing this, because our coordinate system's just looking right at it the whole time. But there would be a lowercase omega that dealt with this motion, you know, and we'd use that to calculate the acceleration that's observed. So, whereas in the first calculation we did, since the coordinate system was fixed, we did see this body moving with an angular velocity relative to our coordinate system. You know, we saw the guy going around once every couple seconds or whatever. And so that's a lowercase omega. We see a circular motion. Now in the second case, we don't see a circular motion. We just see the guy sitting there. And, right, that's right.
So if in this case they're not equal, what's the logic behind justifying the uppercase omega being that?
Okay, so yeah, it's sort of, I think just the words are sort of tricky on this. So yes, the lowercase, this body, whether that body has a coordinate system connected to it or not, this body is moving 0, 0, 3. Okay. In the first way of doing this calculation, that body is moving 0, 0, 3 relative to the coordinate system. The coordinate system sees the body moving 0, 0, 3. In the second one, the coordinate system is moving 0, 0, 3, but the coordinate system doesn't see this guy moving with that.
Because the whole system is
right.
0, 0, 3. In this case, the coordinate system is moving with that system.
Right.
Then, okay, that makes sense.
Yep. Okay, now we have everything, right? So the acceleration is equal to 0, 0, 0 plus 0, 0, 0 plus v observed is still 0 plus 0, 0, 3 crossed with the quantity 0, 0, 3 cross in this coordinate system. Oh, well, we already did that. Position is 5, 0, 0. And so the acceleration is 0, nope, negative 45, 0, 0. So the camera reports their results and they don't see any acceleration. But then, based on what we know about the motion of the coordinate system, it corrects to what we got before. Yep. Okay.
It was a cross product. So
Oh, okay.
the position has a 5,
Okay, yeah. Any questions about that one? It'll get harder. Yeah, there was only one non-zero term in this whole thing. Oh, for sure, that's the hardest part. Yeah. Yes. Yeah. Yeah, exactly. Okay, so now the coordinate system is rotating. And the origin is fixed here. Okay. So is the origin accelerating? Yes, the origin is moving in circular motion. Okay. And the axes are also rotating, so we're going to have to use. Okay, so.
When you said the lowercase omega was 0 because it was moving with the axes, is there a way to like have a rule for that as far as like uppercase minus the original lowercase will always be? Because in that case, the uppercase was the same as the lowercase.
Yeah, you're probably right. Yeah.
So if you had one rotating, let's say like 2 radians per second faster, minus the 2, that way 0 would be.
Yes, you're definitely right. Yep, that's right. Yep. Okay, so now the origin is accelerating. And that means that we're going to have to use, who remembers what you use to deal with an origin accelerating? Motion, yep. So acceleration of the, I lit a fire under Scott when I threatened to shoot him. I like that. I'm going to do that more often in the future. So the acceleration of the origin. Yeah. No, what we want is the acceleration of the object, the astronaut, relative to the ground, is equal to the acceleration of the astronaut relative to the origin, plus the acceleration of the origin relative to the ground. And then this is where the term where we're going to have to deal with the rotating coordinate system. Okay, so first let's figure out the acceleration of the origin relative to the ground. Just in words, what's the motion of the origin? It's in circular motion with an angular velocity of 0, 0, 3. So this is just going to be alpha cross r plus omega cross quantity omega cross r. There's no omega. No alpha, yeah, sorry. Omega is 0, 0, 3. What's r? Exactly, yeah. 2.500 is r. And so acceleration of the origin relative to the ground is 0, 0, 3 cross quantity 0, 0, 3 cross 2.5, 0, 0. And that's just negative 22.500. Okay, so we'll set that aside for later. And then the acceleration of the astronaut relative to the origin. Now we're doing this calculation as if the origin was at rest, but it's still rotating. So here we have to use the equation that says acceleration observed plus capital Omega dot, that's the position vector, plus 2 times capital Omega with the observed velocity vector. Thank you. And then plus capital Omega cross quantity, capital Omega cross P.
Case, first three terms are zero.
Yeah, they are going to be. Yep. That's right. So the observed acceleration, you know, it's still, even though it's halfway down the arm, it's still just a little closer, but just still sees the astronaut sitting in place. So there's no observed acceleration or observed velocity. The position vector is 2.500. There's no change in the angular velocity, so that's zeros. And the angular velocity of the coordinate system is still 0, 0, 3. And so the acceleration of the astronaut relative to the origin is 0. Plus 0. Plus 0. Plus 0, 0, 3. Cross quantity 0, 0, 3. Cross 2.500. And that is negative 22.500. And so the acceleration of the astronaut relative to the ground is negative 22.500 plus negative 22.500, so negative 4500. And so with any of those calculations, you can come up with something you could then use in Newton's second law to calculate the net force or individual forces or whatever. Any questions about that? Okay, so the next thing I want to, let's not do it today, but the next thing I want to do, I just want to introduce it, has to do with polar coordinates. And in polar coordinates, you have this sort of implied underlying coordinate system that's fixed. Okay, but it's not really. I'm using this different color because it's a reference. It's implied to be there, but it never comes up in the calculation. And if you're tracking the motion of a particle that's doing whatever it does, okay, at any instant, the location of that particle is given through the distance from that implied origin to the object and a counterclockwise angle theta from the implied x-axis to that line going from the origin to the object. Okay, so the polar coordinates are r and theta. But that's not a vector. And so to do dynamics, we want to come up with an orthogonal coordinate system where we can represent the position as a vector. So to define position and velocity and acceleration vectors, we're going to choose a coordinate system with the axis ER pointing from the origin to the object. And E theta perpendicular. So here's the coordinate system that we're going to use. That's the axis ER. And then E theta is perpendicular to it so that the third axis would be pointing out to us, according to the right-hand rule. So here's the E theta. Then see if you can think of what the position vector is in this coordinate system. Well, it's super simple. So it's about as simple as you could imagine. Almost. Those aren't vectors. R0. Yep, exactly. Then the position vector is just equal to R times that ER axis plus 0 E theta, or we'll just think of that as R0, where that first one refers to the ER, and that second one is E theta. Yes, that's right. Okay, so to do dynamics, the main thing that you need is to come up with an acceleration vector. So starting with this simple position vector, how would you come up with the acceleration vector? Well, your first stupidest thought would be that you could just take the time derivatives of that. The velocity vector is just r dot 0, and the acceleration vector is r double dot 0. But the problem is, as this object moves around, that coordinate system moves around with it. Okay, and so this is a rotating coordinate system. And so if we just took time derivatives, we'd be calculating the observed velocity and observed acceleration, but not velocity and acceleration that you could use with Newton's laws. This is 0. Because, so look at the coordinate system, like how do you, according to this coordinate system, how do you get from the origin to the thing? You just head straight out along ER, a distance of R, and you're there. But notice the ER, E theta coordinate system is rotating. So for a velocity vector, we're going to have to use let's say, so position R dot, position theta dot, plus capital omega cross the position vector. I'll put a 0 on here too because of these cross products. And the acceleration vector is going to be PR double dot, P theta double dot, 0, plus capital omega dot crossed with the position vector, plus 2 times capital omega crossed with the position R double dot, position theta double dot, 0, plus capital omega cross quantity, capital omega cross P. Yep, thank you. And I think probably, I mean, just depends on what calculus problems you did or whatever, but a lot of you, I think, saw problems in calculus where it talked about the expressions for, just in passing, didn't spend a lot of time on it, but representations of the velocity and the acceleration in polar coordinates. You get these funny, like complicated expressions. Well, this is where those come from. And so on Friday, we'll use this to derive expressions for velocity and acceleration in a polar coordinate system. And it works the same in cylindrical. Spherical is a little more complicated. Okay, that's all.